Hi there, I'm Susan German. I'm one of your facilitators for the S109 Science course. I'm here to kind of give you a recap over the last couple of weeks of some of the larger ideas that we're trying to get across within the course. So one of the first ideas is the fact that science with the next generation science standards, otherwise known as NGSS, those performance expectations brought about some key shifts in how we present science to our students. One of which is the real world connections. And we look at those real world connections under the guise of phenomena often or problems in engineering. The second is shift is the idea of the three dimensions. We have the science and engineering practices, the cross-cutting concepts, and the disciplinary core ideas. All this working together helps students achieve a deeper understanding and be able to apply science concepts into new situations, and that science and the science performance expectations in NGSS are coordinated with the Common Core standards. So the idea of conceptual understanding, that's one of those big broad things. So when we're talking about deeper understandings, this is what we're getting. And so conceptual understanding is where students can grasp ideas in a transferable way. Paige Keeley, my dear friend, was talking about conceptual understanding as the difference between making a cake from scratch without a recipe versus making a cake from a packaged mix. She said when you make a cake from a packaged mix, you can just follow the steps and you're assured of a cake. When you make a cake from scratch with no recipe in front of you, you have to have an understanding of the ingredients and how they interact and how they work together in order to produce a cake that has a good quality, good tasting quality to it. So when we look at that, what we're after here is trying to get to the idea of phenomena. So when we talk about using real world science, we're talking about using events that are observable. Now, I always like to say phenomena is more ordinary than extraordinary. You don't have to look for big things. You can look for events just around in your area, which is what a lot of you did a great job of. When I read through the discussion posts, especially those of you by the lake, you all talked about how using those personal flotation devices as a way of getting students interested and connecting with students, because they have a lot of experience with that due to their location near a large body of water. This next set of slides here is kind of overviews how I've taught it in the past. To students about density, and I've used the idea of a personal flotation device. Mind you, now that I've read all your posts, I need to go through and revise some of the work I've done. So the idea we have with the kids is, how does a life vest keep us afloat? And I have the students develop an initial model, and notice I have just something plain for a container of water, and I use little circles as representation particles that make up water and ones that make up foam. The idea behind some of this is because if we use some general consistent knowledge, so blue and orange, when I look at their pictures, when I'm wandering around the room, I'm able to see fairly quickly what they're trying to convey and ask questions beyond just, what do you mean here? The other part that's not listed in here is we use a call out, but we'll get to that later. So once the kids get their initial models down on paper, it's kind of like getting them to predict, right? So they're trying to explain, why does the foam float? And we use empirical investigation. So one of the empirical investigations is we look at film canisters, and that allows us to compare and I put different things in those film canisters. That allows us to compare how, if we change mass but volume remains constant, what happens. Then we spend some time with creating a graph. We create a graph where we measure the mass of water for 10 milliliters, 30 milliliters, and 50 milliliters, and they make a standards graph. Then I give kids different objects of different masses and different volumes, and the kids plot those objects with the volume on the x-axis and the mass on the y-axis. and they plot those objects, and then they predict what objects they think will sink, which objects they believe will float. The idea being is the objects above that water line are going to be objects that sink, and the objects below that water standards line are the objects that are going to float. So the kids build a conceptual idea that if we have low mass but a larger volume, those are going to be objects that float because that ratio is less than 1, because the slope of the line would be the density of the water. After having some hands-on experience, the students are then able to, I feel more comfortable with them using a simulation. I try and give students as much hands-on direct experience with a phenomena as possible before letting them use a simulation. It just kind of helps transfer the information better. Sometimes though, simulation is the only way you can go, and I totally get that. So now, after we've done some work with these with the Explorer, it's time to pull out our initial models and relook at them. So they evaluate their first thinking, and then they offer revisions to their model. And then we might do some peer comparison and evaluation at that time. So we post the models up in the classroom, and kids can go around and with post-it notes and provide some evaluative comments for the students to help them think about their models. At this point, we're able to construct a consensus model across the class of what we think density is and why a piece of styrofoam floats in water. And then we take this and we start changing our situations, right? So one of our possible extensions is to give the Keeley probe here of solids and holes. So now we've changed the situation. Most all the situations we've worked with, it's a solid object that we've put in. And now we're seeing if they truly understand that when we remove mass because we've poked holes, we've also removed volume. Another extension is going to what we did with that lesson was the life jacket. So we have our peeled orange, and the students look at that, and then they look at develop their life vests for their action figures. And notice that I have marked in red here, determine the density of an action figure without the life vest and with the life vest. So they have to do some math, and yes, there's some estimation going on with this because it's hard to get an accurate volume and it's hard to do all these pieces and parts, but the kids get pretty close enough to where they start seeing how the volume of the object has changed, but the mass doesn't change as much, which allows kids to think about the fact that the density lessens, which keeps our life vest or keeps us afloat. And then here I give some written test question examples related to this. This is one where the kids have to do some plotting, and then I give them an object and they have to plot where that object is and then tell me if it's going to sink or float based off the graph and based off the evidence provided from the graph. Here's another one where I like to do, I take a large object and I put it in one glass of a clear liquid, and I take a small object and put it in the other glass of a clear liquid. And so the large object might sink and the small object floats, and then I switch those cups and I put the small object in the glass where the large object sunk, and I ask if they think the students if the small object will sink or float. And of course they think because it is smaller it's going to float, and it sinks again. So that forces them to really think about the situation. So we have all these things, and so we took a very fast overview of how to take a phenomena and use that phenomena to help kids get an understanding of a concept. And along the way, hopefully you saw some of those science and engineering practices. We used models, we made some investigations, we analyzed and interpreted some data. So we did some of the work a scientist does as they're trying to figure out or explain the phenomena. Then when we gave the problem of designing a life vest, that's when we were more in the engineering world because we had a problem that we had to come to a solution. I put the practices, meaning what do science and engineers do in order to understand or to complete their work. I put those practices next to the mathematical practices, so hopefully you can see some of the crossover. So what mathematicians do and what science and engineers do, there's a lot that's shared in common between the two subject areas. And my goal here is to help you think about possible points of integration. Last but not least, the whole reason that we're doing this is, of course, we want our students to be thinkers. We want our students to achieve in math and science whatever it is that they're going to need in order to be successful in life. So these engineering experiences help students learn the math and learn the science at a deeper level. It provides them some context. Kids use the skills more in depth than they will normally in other situations. And then my personal favorite is this last one here. By trying to solve problems, students discuss math and science concepts. Engineering, for me, the definition of engineering is the application of math and science with judgment. So students have to take their math and science content knowledge and bring that to the table and hopefully interact with each other as they're trying to make a judgment call on the best way to solve a problem. I've tried to keep this under 10 minutes. I'm a little bit over today. I appreciated all your posts very much. Look for an email from me in terms of coming up with a time that maybe we can have on Zoom or Skype or something, that if you have questions, you have a spot where you can go and get your questions answered. By no means would this be a required thing for you to do. It's just something to have available to you. Thank you.